This video lecture is meant to cover the information that is found in Chapter 12. This is Unit 11, and the unit is called Stoichometry, and stoichiometry is essentially the measurements that are involved in chemical equations. So, revisiting a chemical equation, we need to remember how to interpret it and what coefficients mean in a balanced equation. Here we see nitrogen gas reacting with hydrogen gas to form ammonia in the ratio of 1 to 3 to 2. Now, what do those numbers represent a ratio of? Well, they can represent the number of molecules. So you could say that one molecule of nitrogen will react with 3 molecules of hydrogen gas to produce 2 molecules of ammonia. Alternatively, the coefficients can also represent the number of moles, remembering that a mole is just a certain number of molecules. One mole, of course, is equal to 6.02 times 10 to the 23 particles, or molecules. So really, moles is just a very specific number of molecules, which is why those coefficients in a balanced equation can also represent a mole ratio. So for every 1 mole of nitrogen particles, you need 3 moles of hydrogen particles to produce 2 moles of ammonia particles. However, the number of grams are not represented in the ratio because for every 1 of these nitrogen molecules, that will weigh different than 1 mole of hydrogen molecules. So if we were to measure out the number of grams represented by 1 mole of nitrogen, that would be equivalent to 28 grams. And of course, we're getting that from the periodic table. Nitrogen's atomic mass is 14, but there are 2 of them. If we were to figure out the mass represented by 3 moles of hydrogen, 1 hydrogen molecule is 2 grams, so 3 moles would be 6 grams. So you would need 28 grams of nitrogen to react with 6 grams of hydrogen. This will produce 2 moles of ammonia. Well, 1 mole of ammonia weighs 17, so 2 moles weighs 34 grams. So what we see here, 28 to 6 to 34, is not a 1 to 3 to 2 ratio. So the number of grams is a different ratio than the mole ratio, the molecule ratio. But an interesting thing to notice here, since these 2 represent the reactants, and this represents the products, please take notice that 28 plus 6 is equal to 34 grams. So this confirms the law of conservation of matter, and which essentially means that the mass of the reactants has to equal the mass of the products. You cannot create matter, you cannot destroy matter. Well, let's take a look at some problems that we will use to capitalize on this idea. Considering the following balanced equation, it's a 1 to 3 to 3 ratio of ozone and nitrogen monoxide and nitrogen dioxide. First question says, what is the molecule ratio of these chemicals in this reaction? So just like you just saw, we're taking this number, and this number. It's 1 to 3 to 3. So using that ratio, how many molecules of NO2, that's this, could be produced from 25 molecules of O3? Okay. So if you have 25 O3s, ozones, how many NO2s will that make? Well, it's a ratio of 1 to 3, as we see here to here. So 25 molecules of O3 will give you 75 molecules of NO2 because of the 1 to 3 ratio. Part C says how many molecules of O3 are needed to react with 1.81 times 10 to the 24th molecules of NO. I'm going to erase this right here so we can see this a little more clearly. So now what this question is asking in 1C, how many molecules of O3 are needed to react with 1.81 times 10 to the 24 molecules of NO? So this is a 1 to 3 ratio, and if it's not a mental math problem, like this one may not be, you can see that we can set this up as a conversion fraction. So if you start with 1.81 times 10 to the 24 molecules of NO, setting up a conversion fraction so that molecules of NO cancels out in the denominator, and molecules, molecules of O3 in the numerator. The numbers that go in here are the coefficients from the balanced equation, right? If you notice 1 molecule of O3 to 3 molecules of NO, and now your math just becomes 1.81 times 10 to the 24 times 1 divided by 3. And you will see here that that gives you 6.02 times 10 to the 23 molecules of O3. Let's take a look at question number 1D. How many moles of O3 are needed to react with 3 moles of NO? How many moles of O3 are needed to react with 3 moles of NO? So this problem, it goes back to the idea of mental math. If you have 3 moles of NO, you're going to need 1 mole of O3. You could set this up if you were trying to show your work. You would start with the number given, 3 moles of NO, set up a conversion fraction, moles of NO in the denominator, moles of O3 in the numerator, 1 to 3, those numbers come from the coefficients from the balanced equation, and so there you get your 1 mole of O3. So what we can see here in a balanced equation, the coefficients represent a ratio of the number of molecules as well as the number of moles. But what the balanced equation, what the coefficients do not represent, it's a ratio of grams. Let's take a look at problem number 2. Consider this following balanced equation. This is the combustion of octane. 2 molecules of octane react with 25 molecules of oxygen gas to produce 16 molecules of carbon dioxide and 18 molecules of H2O. The first question is asking how many moles of water can be produced if 50 moles of oxygen gas are consumed. So I'm going to start with the number given, 50 moles of oxygen gas. I'm going to put moles of O2 on the bottom because that's what I'm trying to cancel, and moles of water on the top because that's what I'm trying to find from the balanced equation. 18 moles of water, 25 moles of oxygen. In your calculator, this is 50 times 18 divided by 25, or you might have been able to see that 50 divided by 25 is 2 times 18. Either way, you come out with 36 moles of water. Question 1b. Burning 8 moles of octane will produce how many moles of carbon dioxide gas? So we're going to start with octane, and we're going to try to figure out how many moles of carbon dioxide gas. So starting with a number you're given, 8.0 moles of octane. We're going to use moles of octane in the denominator, so it'll cancel out. We're going to put moles of CO2 on the top, and carbon dioxide coefficient is 16. Octane coefficient is 2, so this is 8 times 16 divided by 2, which gives you 64 moles of CO2. Part C. How many moles of oxygen gas are needed to burn 14 moles of octane? So the problem gives us 14 moles of octane to begin with. So moles of octane goes in the denominator. Moles of O2 goes in the numerator. The coefficients for oxygen is 25, for octane is 2. So this is 14 times 25 divided by 2, which will give you 175 moles of oxygen. All right, let's take a look at problem number 3. Consider the following balanced equation. And you certainly could not do these problems until you balance the equation if you were given an unbalanced equation, but we are starting with balanced equations. This question says how many moles of aluminum sulfate could be formed from 0.442 moles of aluminum chloride. Okay, so this is the aluminum chloride, this is the aluminum sulfate. So to do this problem, you start with the number you're given, 0.442 moles of the AlCl3. Your conversion fraction should put moles of AlCl3 in the denominator and moles of Al2SO43 in the numerator. Now your job is just to attach the numbers. 1 mole of aluminum sulfate, because the 1 is understood right here, over 2 moles of aluminum chloride, because that's the coefficient there. And so your math is 0.442 times 1 divided by 2. That gives you 0.221 moles of Al2SO43. Part B. How many moles of nickel sulfate will react with 6 moles of aluminum chloride? Okay, so now we're dealing with aluminum chloride and the nickel sulfate. Starting with a number you're given, 6.0 moles of AlCl3. Set up a conversion fraction. Moles of AlCl3 in the denominator. Moles of NiSO4 in the numerator. Now go to your equation, get the coefficients. For NiSO4, the coefficient is 3. And for aluminum chloride, the coefficient is 2. So your math here is 6 times 3 divided by 2, and you will get 9 moles of nickel sulfate. Part C. If 9.3 moles of nickel chloride were formed, how many moles of aluminum sulfate were formed? So now, going back to our equation, we're dealing with the nickel chloride and the aluminum sulfate. So let's start with the number we are given, 9.3 moles of NiCl2. So moles of NiCl2 goes in the denominator. Moles of Al2SO43 goes in the numerator. The coefficients are 1 and 3, so the math is 9.3 times 1 divided by 3, and you will get 3.1 moles of Al2SO43. Okay, let's take a look at the last problem. Number 4, consider this balanced equation. This is the combustion of methane. How many moles of carbon dioxide can be produced from 6.7 moles of methane? So we're dealing with methane in this problem and carbon dioxide. Now you might notice they're in a 1-to-1 ratio. So you should automatically be thinking mental math here. You're just going to get 6.7 moles. If you were asked to show your work, you would set this up with the number you are given, 6.7 moles of methane. Moles of methane goes in the denominator. moles of carbon dioxide in the numerator. It's a 1-to-1 ratio, so the math goes to 6.7 times 1 divided by 1, giving you 6.7 moles of CO2. So that's how you would show your work on how to convert that unit. Part B, how many moles of oxygen gas are needed to react with half of a mole of methane? All right, so now we are dealing with methane and oxygen, which is in a 1-to-2 ratio, starting with the number you're given, half of a mole of methane. So moles of methane goes in the denominator, moles of oxygen goes in the numerator, 2 over 1, so now 0.5 moles times 2 divided by 1 just gives you 1.0 moles of O2. And the last problem, stop for a moment and think about your answer to question 4B. What if I had asked you how many grams of oxygen gas would this be? Well, now you're just taking that answer of 1.0 moles of O2, and now we have to convert that to grams. So this is a periodic table molar mass question. Start with the number you're given, 1.0 moles of oxygen. So moles of oxygen goes in the denominator, and we want to know how many grams of oxygen that is. Well, remembering back to your molar mass conversions, it's always 1 mole of oxygen is equal to some mass. And if you consult your periodic table, you'll know that the mass of oxygen is 16.0, but since it's O2, our molar mass is 32.0. So here we see that we will have 32.0 grams of O2 created. And so this is where this unit will be going next. We will not always have simple mole-to-mole ratios. We will factor in the masses of the starting substance and the masses of the substance you're trying to find out. And so what you'll hear me calling this information is what you learned today is mole-to-mole stoichiometry. The next step is gram-to-gram stoichiometry, and that'll involve a few more conversion fractions. But for right now, this is mole-to-mole stoichiometry. There is a homework problem set for you to try, and take a look at that, see what you can do with it, and we will see you in the classroom.